Hi there, welcome to your lesson on binomial distribution. Notice we have here two paths, one to failure, one to success. There are two choices, therefore binomial distribution. Great lesson, let's get started. Let's begin with a little flashback on some things we've seen recently. First is the difference between discrete and continuous data. Discrete data is either data that can be counted, for example, the number of cars in a car park, or data that can only take specific values, for example, shoe size. Continuous data can be measured. For example, height, weight, and time are all continuous variables. Okay, so here's an example. We have at a coffee shop, there are 4 percolators, these machines for making coffee. Let's let random variable b represent the number of percolators that breaks in one day. Is this a discrete or continuous variable? It's definitely discrete because you can only have a certain number, a specific value of broken percolators. So what values can this discrete random variable take? Well, it can be, B can be 0 broken percolators, 1, 2, 3, or all 4 break in one day. So there's a set of possibilities and you can see it's discrete. All right, let's take the coffee analogy a little bit further. Let's say we know that coffee bags weigh from 0.98 to 1.03 kilograms. Let's let random variable W represent the weight of a coffee bag. Is this a discrete or continuous variable? Well, W is definitely continuous because the weight can be any number in between these two values here. It can be measured. What values can it take then? Well, W can take any values between 0.98 and 1.03 inclusive, so we can show it like this. We can't list it like we did here, but we can show it's within this range of values here. All right, so going on from there, again, B is the number of percolators that breaks in one day. There's our set of possible B values. We know that this is a discrete random variable, and we can represent the probabilities of each outcome in something called a probability distribution table. So here we have 0 broken percolators, or 1 or 2 or 3 or 4, and here's probabilities of each of those things occurring. So for example, the probability of there being 2 broken percolators is 0.06, and we can see it right here in the table. So again, this is a probability distribution table for a discrete data set or discrete random variable. It can be represented on a bar graph. Here's all the probabilities, and you can see the bars are not connected because this is discrete data. All right, with that, let's recap something we saw a little bit further back, something we saw way back earlier in the course called combinations. Here is a combination formula. We sometimes say n choose r or n choose r like this, and we know that the formula tells us we have n factorial divided by r factorial times n minus r factorial. And factorials just mean multiply a number by decreasing values. If you go to consecutive numbers in decreasing integers, those are the multiplications you do. For example, if we had 5 choose 2, that would be written like this. 5 factorial following this formula over 2 factorial and then 5 minus 2 factorial, which is actually 3 factorial. Then again, factorial just means you multiply consecutive whole integers like this, and you have 5 times 4 times 3 dot dot dot. And on the bottom, 2 times 1, and over here this becomes 3, so 3 times 2 times 1, etc. We know when we have combinations, we can cancel things. For example, 3's and 2's and 1's cancel. You're left with just this. That means 20 over 2, which is 10. So some combinations we can work out pretty quickly just by knowing how the rule works. Others we might need our calculator. But we also saw a very important connection between combinations and what is called, or what is known as, Pascal's triangle. We found out that for a certain row in Pascal's triangle, you can get every value in it using combinations. For example, if you did 5 choose 0, you would get 1, and that matches this value here. If you did 5 choose 1, you would get 5, which matches this value here. And if you did 5 choose 2, you would get 10, which matches this value here. So this would be 5 choose 3, 5 choose 4, 5 choose 5. Notice we start with 0, and we begin with 0 there. So that's an important connection we saw earlier in the course. We're going to use this now in this lesson, so let's keep moving ahead. Okay, so we are ready to talk about the binomial distribution. Binomial distribution models things such as this. For example, let's say we toss a coin 2 times and we are trying to attain as many heads as possible. So here is a tree diagram representing that coin toss situation. Here's the first toss, here's the second toss. And we can get either a head or a tail when we toss the coin, and then there's the same probability to get a head or a tail, 50-50, half or half. And then on the second toss, probabilities remain the same. Again, we can get head tail or head tail. Okay, great. This path on top leads to 2 heads, this one leads to head tail, this one leads to tail head, and this one leads to 2 tails. So that's something we've looked at in probability, but now we're going to take this and look at it from the lens of binomial distribution. Binomial distribution, for something to be binomially distributed, it needs to meet these 4 criteria, and they are: number 1, there is a fixed number of trials. And we can see that in our situation. The number of trials is 2. There are 2 coin tosses occurring. It can be 3 or 4 coin tosses, whatever, but there's a fixed number of trials. Great. Condition number 2, each trial has only 2 possible outcomes. So along each trial, so in this case each toss, there's only 2 outcomes, a head or a tail. And often in binomial distribution we call it a success or a failure. If it said we're trying to attain as many heads as possible, we can say head is a success, tail is a failure. So there are only 2 things that can happen, success or failure on each trial. Okay, great. Our situation meets that condition. Condition 3, the probability of success is constant. All right, so that means the probability throughout the trials, the chance of getting a success is always the same. And in this case, that's true. The chance of getting a head, which we're calling a success, is always the same. 50% chance here, 50% again. If we had more trials, it would be 50% each time. Constant. Great. Condition number 4, trials are independent of one another. What that means is, after you're done the first trial, in this case the first toss, the probabilities remain unchanged. There's no dependence. Like these probabilities don't depend on what happened here. If you got a head here, these probabilities are the same as if you got a tail first. That does not influence what happens next. Great, we meet those 4 conditions, so this coin toss situation is a binomial distribution. So let's get deeper into that now. So let's say again we have a fair coin tossed twice, which is what we just talked about. We're going to let x be the discrete random variable equal to the number of heads that are tossed in 2 trials of the fair coin. Use a tree diagram to represent this. Well, we saw that already, so here's the tree diagram. Now we're going to fill this probability distribution table. So again, x represents the number of heads, so this means 0 heads, 1 head, 2 heads. So what's the probability of getting 0 heads? Where is that path on here that shows 0 heads? Well, the 0 heads path is the one on the bottom because it leads to 2 tails, right? 2 tails means 0 heads have occurred. So what's the probability along that path? Well, if you multiply a half by half, you get 1/4. Okay, next, let's go to this one here. What's the probability of getting 1 head? Well, are there multiple paths? Yeah, in this case there are. The 2 middle paths lead to 1 head because this is head tail and this is tail head. So both of those lead to 1 head. So to find the probability of getting 1 head, you have to add the probabilities along both paths. So what is it? Well, that number is 2/4 because each path has a probability of 1/4, and now we have 2 quarters together, which is 1/2. And finally, what's the probability of getting 2 heads? Alright, clearly that is the top path. You multiply along those branches and you get a probability of 1/4. Notice these all add up to 1, as they should in every probability distribution, but also notice that in this case we have this happening. Okay, so there is 1 path out of 4 paths that lead to no heads, so we have 1 out of 4. There are 2 paths out of 4 paths that lead to 1 head, so we have 2 out of 4, and there's 1 path out of 4 that leads to that. But I want you to be aware that this idea about how many paths lead to there and that becomes our probability only occurred here because the probabilities are equal. It says 50-50. If these were not equal probabilities, we cannot simply count how many paths there are and say that's our probability. We would have to add up the probabilities along the paths, right? Okay, so let's keep going with this a little bit further. Let's see some important connections. So we have this coin tossing situation, and we know how many paths lead to each outcome. So how many paths lead to 0 head, 1 head, or 2 heads? Let's recap again. Okay, we know those numbers are 1, 2, and 1, right? One path here to 0 heads, one path to 2 heads, and then 2 paths to 1 head. That's what we just talked about. Great, that's how many paths we have. Now, what connection do you see to Pascal's triangle? So here's a bit of Pascal's triangle. Do you see a connection? Okay, I think the connection is pretty obvious in this case. We see these number of paths here, and they match this row in Pascal's triangle. This is not coincidental, and this is key to what we're going to be looking at here. So we see 1, 2, 1, 1, 2, 1. So row 2. Notice the number of paths leading to each outcome can be found in the matching row number. So we had 2 trials occurring here, so we go to row 2 in Pascal's triangle. 2 trials means row 2, and then we have all the possibilities here. Great. So let's keep going a little bit further with this. So now that we know that, what is the probability of obtaining 1 head? Well, we already talked about that in the probability distribution table, but let's look at it from the lens of paths again. So we can say there's 1 path leading to 1 head, there's another path leading to 1 head. Therefore, we have 2 paths, and each path looks like this. 0.5 times 0.5, which is a half times a half, right? So we have this probability times 2 because there's 2 paths, right? That's the same as adding those 2 paths. So that leads to this result. Notice the 2 paths can be written by a combination, and this is the key idea here. This is a combination. The combinations, we know, again, produce these values, right? This is 2 choose 0, 2 choose 1, and 2 choose 2. We know combinations produce these values. So we can say, well, if we need to figure out how many paths there are, we can just run a combination. This is a really big idea here. All right, so that works out to 1.5, which we already know. Half the paths lead to that situation. So here's the table we created before, and we can see that this matches what we have here. Okay, great. Good thing to see. Let's move on from there to a more typical situation, because it's very unlikely that when we're talking about binomial distribution that we'll have situations where the probability of success and failure are the same. So let's represent that using a biased coin. That means a coin where you don't have the same chance to get a head and a tail. So let's say we have this situation. Here's a biased coin tossed 3 times. 1 toss, 2, and 3 tosses. And notice the probability of getting a head this time is 2/3, and the tail is 1/3. So let's say now heads again is success. We have a 2/3 chance of success and a 1/3 chance of failure. So now it's a biased coin, and everything will change as a result of this. But the underlying ideas that we just looked at will remain the same. So let's take a look what we have here. First of all, how many paths lead to each outcome this time? And this time the outcomes are we can have 0 heads, 1 head, 2 heads, or 3 heads. So now we have an extra option here. Because of the extra coin toss, we can now end up with 3 heads. For example, on top here, head, 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 that's a path that leads to 3 heads. So what numbers go in here? In other words, how many paths lead to each of these outcomes with the heads? Let's check our work here. 1, 3, 3, and 1. So again, the 0 heads path is the one down here, because that's tails, tails, tails. And that means there will be 0 heads, but there's only one path that's like that leads to 0 heads. Every other path has at least 1 head in it, right? So we can say, and again, 3 heads, there's only one path like that. The top path there, head, 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 there's only one path like that leads to 3 heads. But altogether here, if we count the ends here, we have 8 paths in total. So we've counted 2 of them. That means there must be 6 remaining, these 6 middle paths. And these ones are either 1 head or 2 heads. And each of those has 3 outcomes. 3 of these paths lead to 1 head, and 3 of them lead to 2 heads. Hope you got the same numbers. Now let's check if that matches Pascal's triangle as well. So we saw a moment ago that row 2 showed us all the outcomes in the last situation. Now we're talking about 3 trials. So we're looking at row 3 right here. And row 3 we can see matches what we have here, which is amazing. All right, this is the very key here, right? The row tells us how many paths lead to each outcome. And again, these numbers here can be calculated using combinations. So we never have to look at Pascal's triangle to figure out how many paths. We can just say, hey, I can use a combination, and it'll tell me how many paths lead to that specific outcome. And that's going to be central in calculating probabilities. So what is the probability along the HTT path, the one where you have a head, a tail, and a tail? Okay, so you're trying to find the probability along the HTT path, so that's heads, tails, tails. So find it now. Okay, the probability is found by multiplying the probabilities along the branches. So you multiply 2/3 times 1/3 times 1/3 to get 2/27. Okay, next question. What is the probability of obtaining one head? Well, isn't that what we just found? We found the probability of getting one head. Oh, no, 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 but there's more paths that lead to one head, right? We found out there's 3 paths. So what's the probability of obtaining one head? Well, it is the sum of the 3 paths. Here's another one head path, tails, heads, tails. And here's the third one, tails, tails, heads. So those are the 3 paths that lead to one head. We can again see right here, 3 of them. Now, you can just do 3 paths times the probability we just found right here, which is 2/3 times 1/3 squared, right? So we're starting to create an important formula because again, we know this 3 paths can be obtained if we didn't have the tree diagram or we didn't have Pascal's triangle. How can we get this number? Well, again, these numbers are obtained using combinations. So we could have done 3 choose 1. That means row 3, or we have 3 trials, and we want 1 head. 3 choose 1. And then we know the paths look like this. Every one of the paths that leads to 1 head looks the same because all of them have 1 head, which is 2/3. All of them have a 2/3 in there, and all of them have 2 1/3, which are the 2 tails. Doesn't matter what order we rate these in, the paths all look identical. So we have 3 paths that look identical like this, and that's our full probability of obtaining 1 head. Now this brings us to our key formula for this lesson. It is the binomial distribution formula. And here's how it works. I'll show you now. So we can say a random variable, so discrete random variable x, like we have here. And this symbol means here it's distributed. It's distributed binomially, okay, binomially distributed with n trials. This shows you the number of trials and probability of success p. Okay, so this is how we write that something, a random variable, is distributed binomially. And here is the formula we're going to use, the one we just kind of came up with. It's going to look a little complex here, but we'll see it in an example in just a minute, and you'll see it's not complex at all. But basically, if we want to find the probability of some value for the random variable, then we do a combination multiplied by probability of success to that power, and then probability of failure to this power. Again, this looks a little strange or complex perhaps now, but let's take a look through an example. It'll make a lot of sense in just a sec. All right, so we had the example of tossing a biased coin 3 times we were just working at. Is that a binomial distribution? Well, let's check first because there's these conditions, right? Conditions of a binomial distribution are that there is a fixed number of trials. When we did the coin toss, did we have a fixed number of trials? Yes, we tossed it 3 times. Okay, next. Each trial has only 2 possible outcomes. Did we only have 2 possible outcomes on each trial? Yes, we did. Either a head or a tail. Great. Next, the probability of success is constant. In our biased coin case, the probability of success was 2/3, and that remained the same for every trial, so it's constant. Perfect. And number 4, trials are independent of one another. That means the probability does not depend on what happened before, and it doesn't. It was constant throughout. Perfect. So our situation is definitely a binomial distribution. Therefore, we would write it like this. Our random variable x, which means all the possible outcomes for how many heads we got, is binomially distributed, 3 trials, 3 coin tosses, and the probability of success was 2 out of 3. Great, that's how we would write that. And now let's do an example where we calculate that. So here's our tree diagram for that, and let's say we were asked to find this, the probability of 2 heads obtained when flipping a coin 3 times. So we want to know the probability of getting 2 heads. We could of course draw the tree diagram like we did, we could find the paths, multiply everything, but the whole purpose of the binomial distribution formula is that it allows us a shortcut. Imagine we had a giant tree diagram, we wouldn't want to do this by hand drawing it and calculating every path. So what we discovered is, to find the probability of getting 2 heads, we found out first we need to know how many paths there are that leads to 2 heads. And we can find that by doing a combination. 3 trials, we want 2 heads. That combination will tell us how many paths on here will lead to 2 heads. And actually that is 3 paths. We can check it here. And then we multiply by what each of those paths looks like, right? So each of the 3 possible paths looks like this. If we're going to get 2 heads, we're going to have head, head, for example, so 2/3 times 2/3, so it's always the probability of success, and then how many times you want that success to occur is 2/3 to the second power, because there'll be 2 of those in your multiplication. And then if you have 2 heads, there must be a tail, so a 1/3. So that's the probability of failure here, and that's one of those in the path. So again, this tells us there will be 3 paths, and each of the 3 paths will look like this, where you have 2 heads followed by 1 tail, and the order of this doesn't matter. That is the binomial distribution formula that's going to help us. All right, so that works out to 3 paths, and each path looks like this, and therefore our probability is 12/27. It's that easy. It really is that easy.